Look inside the phone in your hand, and you'll find a hidden world. Stripped of its sleek glass and metal shell, you're left with a dense, glowing green landscape. It looks intensely complicated, but everything on this board, and inside every electronic device you own, is built from the exact same handful of simple, repeating parts. The easiest way to understand how electricity moves through this landscape is to imagine water flowing through a system of pipes. In this plumbing system, the actual amount of water moving past a certain point is the electrical current. The physical pressure pushing that water forward is the voltage. If you can map how that water flows, bends, and builds pressure, you can decode how almost any piece of electronics on Earth actually works. Before we start adding complex machinery to our pipes, we need to look at how the pipes themselves are arranged. There are two basic ways to lay them out. A series circuit is a single loop. Water flows through every component, one after another. If a wheel jams, water stops everywhere. In a parallel circuit, the pipe splits into branches. If one wheel jams, water bypasses it and keeps flowing. In a series setup, every component shares the exact same flow of current. But in a parallel setup, the pressure, or voltage, is shared across independent paths, making the system much more resilient. Now that we have our pipes laid out, we need to control the water. We do that first with a resistor. You can think of it as a speed bump for electricity. Delicate parts like LED lights will burst if they get hit with too much pressure. A resistor physically pinches the pipe, choking the flow and slowing the rushing water down to a safe, steady trickle. Next, we have the capacitor. Instead of slowing the water down, a capacitor acts as a temporary storage facility. Imagine a tank with a flexible rubber membrane in the middle. When a sudden surge of water hits, the membrane stretches out, absorbing the excess pressure. Then, when the flow drops, it snaps back, releasing that stored water to keep the stream perfectly level. Together, resistors and capacitors act as the core stabilizers. Without them, our delicate electronics would constantly fry from sudden power spikes or instantly shut down the moment the pressure dropped. Our next component, the inductor, also stores energy, but instead of a physical tank, it holds energy in a magnetic field. Think of an inductor as a massive, heavy water wheel. It takes a lot of effort to get it spinning, and once it is, it's very hard to stop. Because of this momentum, an inductor fiercely resists any sudden changes to the speed of the current. While inductors manage momentum, we also need to manage direction. A diode acts as the ultimate one-way street sign. It behaves exactly like a mechanical check valve. It swings wide open to let water flow forward, but slams tightly shut if the water tries to rush backward. If you combine multiple diodes together, you create a rectifier. This arrangement forces chaotic, back-and-forth alternating current, the kind pouring out of your wall outlet, into a neat, continuous one-way stream. There is a special exception called a Zener Diode. It stays shut like a normal diode up until the pressure gets dangerously high. At that breaking point, it forces itself open, acting as an emergency relief valve. While resistors and capacitors adjust the amount of power, inductors and diodes enforce the rules of the road. They control the behavior and direction of the flow, making complex systems possible. All of those parts set the stage for the component that makes truly smart devices possible, the transistor. A transistor is essentially a power-operated valve with three parts. A tiny trickle of water at the control pipe pushes open a gate, allowing a much larger rush of water to flow straight through from the intake to the outlet. Because of this design, a transistor has two distinct abilities. You can use that tiny trickle to turn the gate fully on and off, like a digital switch, or you can use it to smoothly amplify a tiny signal into a larger one. Over time, engineers created a more modern version of this valve that is even more efficient. Instead of needing a constant physical trickle of water to hold the gate open, this version triggers the switch using only sheer electrical pressure. It requires almost zero flow to maintain, making it incredibly fast. By linking these switches together, we create paths for information. If a switch is open, the device reads a yes. If it's closed, it reads a no. Chaining billions of these simple yes or no choices together is how a circuit board makes decisions and processes information. Let's leave our plumbing system behind and look back at the real thing. All those little components suddenly make sense. You have the resistors, capacitors, and inductors, carefully shaping and stabilizing the raw energy. You have diodes strictly directing the traffic, and millions of microscopic transistors firing on and off to make high-speed logic decisions. Decades ago, creating these precise circuits required massive testing equipment and rows full of exposed, tangled wiring. Today, we fit billions of these components onto slices of silicon no larger than your fingernail. Those microscopic parts are charging, switching, and routing power billions of times per second right now, inside the exact screen you are using to watch this video. It looks like pure magic from the outside, but once you see the pipes, you realize it's a perfectly balanced system of managed flow.